Hello, my name is Tdikici. Today I will present the Floyd Walsh algorithm for finding the shortest path between every pair of the location in the network. And I will explain what problem it solves and how method works step by step, how we rebuild actual routes and how we notice harmful negative cycle, how long method takes, and when it's right tool to use it. Okay, so what problem are we solving and why does it matter? We are given directed network where each connection has a cost. Um, some costs can be negative, but network should have a loop with a total negative cost. Our goal is know the smallest travel cost for from every starting point to the every ending point. To be able to print the path itself, it is useful in routing, communication, networking, scheduling, and many other planning problems where we need answer for many pairs, not just one source. So the big idea is the method improves all the pairs in organized runs. We line up the network points and allow them as possible way points one by one. In each round, we ask the same question for every pair. If we pass through the current waypoint, do we get the cheaper trip than what we already have? If yes, we keep the cheaper cost and remember how we got it. By moving through the list of waypoints, table of the costs only gets better, never worse, until no further improvement is possible. So slide 4. On the slide there are two rows that shows algorithm in action. In the top row, you see the starting solution. The table on the left holds the initial travel cost. That null is 0 point because the cost from the point to itself is 0. Where there is a direct connection, we place its cost. Where there is a no connection, we mark it as unreachable. The table on the right is helper table that will let us rebuild the routes at the beginning of its knowns about the direct neighbors. The algorithm then runs several rounds. In each round, we test every pair to see whether passing through the current waypoints gives a cheaper trip. When we find a cheaper trip, we update the cost to the left table and we update the helper entry in the right table so we can later print the route. In the bottom row, you see a later round after several waypoints we've been allowed. The highlighted entry shows a place where the cost just improved because going through the current waypoint beat the older value. Using the updated helper table, we can now read an actual route from point C to point B as C to D, A to B, which is shown at the bottom of the slide. Two reminders from this slide. Because we check every pair, we could round. Um, Time grows with the cube of the number of the points. Because we keep a two-square table, the memory use grows with a square of number of points. Slide 5. So to print the route between 2 points, we follow helper table like road sign. And start of the source, look it up. Next, hoop towards the destination. Move there and repeat until we arrive. This follows exactly the chain of improvement that algorithm discovered. If there is no route, the helper table tells us away because there is no next hop to the follow. So negative costs by themselves are fine. After all the routes finish, we look at the diagonal of the cost table. If any diagonal value is negative, that means there is reachable loop with a negative total cost. In case there is no meaningful smallest route for a pair that can reach the table loop, because going around the loop would make the cost smaller. And smaller when we do not see negative diagonal entry, we are done. All smallest costs are correct. This method is a great choice when network is dense, when we are truly need a result for all the source destination pairs. When the network is very sparse and the costs are never negative, running a single source method many times can be faster. For sparse network that includes negative cost, a method that rebates edges then uses the single source search can be better fit. So if you want, I can drop these lines directly into the notes area for questions. And last part, I am happy to answer if you have any questions. Please reach out to me via my email, tdikici@bu.edu. This is a very great semester, and I was very happy to present my final project. Please reach out to me for any questions you have. Thank you for listening.